right, we're going to continue talking about sequences here, and we're going to look at a couple of examples, and then we're going to start working on a really nice theorem that's going to make finding the limits of sequences quite a bit easier. So first, a couple of examples of applications. In example 3, we're told a doctor prescribes 100 milligrams of an antibiotic every 12 hours. Now this drug has a half-life of 12 hours. We'd like to first of all find the recurrence relation for a sequence that gives the amount of the drug present immediately after each dose is taken. And then we'll use our sequence to determine the steady state amount of the drug, that is, how much is going to be present after a long, long time. So here we go. Let's start with the recurrence relation. I'm going to say a sub n plus 1 is going to be calculated based on the previous amount. Well, let's see. Since this is every 12 hours, we have a half-life, and we're doing a new calculation every 12 hours. That means that however much was present before, a sub n has now been cut in half. Right? That's what half-life means. But this patient is also taking another 100 milligrams, so we have to add 100 to that. So the half-life, every 12 hours, the amount gets cut in half, and we add 100 more milligrams. All right, let's take the limit as n goes to infinity here, since we want to now determine the steady state amount, that is after a long time. So if I take the limit on both sides of this little equation, what I'd like to say is, let's assume, I'm just going to put a letter to this, that the limit for the sequence is called some value L. This is our steady state amount. That means that the left-hand side is going to approach L, because this is just the terms of the sequence, right? And this a sub n also approaches L. So I'd have L over 2 plus 100. Okay. Again, I know one of these is a sub n plus 1 and the other is a sub n. But ultimately, as n goes to infinity, the difference between, a billion and 1 is negligible. They're both going to the same limit, L. Well, I now just have a nice little algebra equation to solve, right? If I double both sides, I would have 2L equals L plus 200. And subtracting the L equals 200. So the steady state amount, or the amount of antibiotic in this patient's body after a very long time, remains stable at about 200 milligrams. And that's really the goal anytime a prescription is given, right? After you take this prescription for several days, ultimately the amount kind of levels off and stays steady. It doesn't keep on increasing indefinitely. All right, let's take a look at example 4. Marie takes out a car loan of $20,000. The bank charges 6% interest, and of course the interest rate they charge you is actually an annual interest rate. And it assesses a 0.5% interest monthly, right? So that's just 6 divided by 12 to give the monthly interest rate. They assess this interest just before Marie makes a $400 payment, which she also makes monthly. Write a recurrence relation for a sequence that gives the loan balance each month. And then this time we're going to use a calculator to determine the lifetime of the loan. How long is it going to take her to pay off the car? So let's start with the recurrence relation. The loan balance, a sub n plus 1, in a subsequent month, we would calculate how? Well, first of all, we take the previous loan balance, A sub n, and we have to charge that 0.5% interest. So we multiply that by 1.005. 1 because we keep the full amount plus that 0.5% interest. But then Marie makes the $400 payment, so the loan balance is also going to decrease by $400 each month. So it goes up a little bit because of the interest, but down because of what she pays. So there's our recurrence relation. Now we don't want to let n go to infinity. Poor Marie is not going to pay this bill off forever, right? We instead want to know, what should n be? How many payments is she going to make by the time this loan is paid off? Or in other words, by the time the balance is 0. That's not an easy question to answer pencil and paper, but fortunately our calculator can help us with it. We haven't yet talked about how to enter a function, a recurrence relation like this into the calculator, so this is a good time to do that. Instead of a, the calculator gives me u, but it's the same thing. And we're going to go ahead and say, yeah, the minimum n value here is going to be 1. And we're going to then say, actually, you know what? We should really start here with 0. Because at time 0, she still owes the $20,000. She hasn't even made that first payment yet, right? So let's start with 0. Our function u sub n is going to be this. And we're going to have to write this just a little bit differently. Notice that instead of n plus 1 here, they're always just going to have, it's really like a u sub n. So I'm going to fix this. I'm going to say, what if I went with n here and n minus 1 there? Would that make sense? It's the same difference, right? Instead of going from n to n plus 1, we're just going from n minus 1 to n. And you know what? As soon as I make that change, I actually have to go back up and change this again too. Oops, didn't mean to do that. Let's get that back again. I need to go back up here and say, all right, I now want to start with an n of 1, because then 1 minus 1 is really the 0th payment when she's first taking out the loan and hasn't made any payments. So here we go. We're going to go ahead here and say u sub n is going to be u sub n minus 1. So second u, notice the u is above the 7 key. That little lowercase u for that u is above my 7 key. So second u of n minus 1 times 1.005 minus 400. And when n is 1, I would have 0, and then that's the full amount. And so I now have to tell them that u of n minimum is going to equal the $20,000 that we started with in the loan. So there's a recurrence relation in the calculator. And again, just useful noting, instead of n plus 1 and n, they're always going to go with n, meaning you'll always have to go with n minus 1 when you type it in. All right, let's graph it. By the way, I've already got my window set up for this one. I went ahead and said I don't think poor Marie is going to end up paying for more than 80 months. So I went from 1 to 80 on her payments. Starting at 1, step size of 1. 1 to 80 on the x's with a scale of 10. And then my y's, I went from negative 10,000 to 20,000 with a scale of 1,000. And there we go. You can see all those little dots representing the payments. I'm going to trace this. And what I'm looking for is when the loan amount becomes 0. Right? She still owes $5,200. Still owes $1,800. Here we're going close though. Ah, there it was. All right. After she's made the 58th payment, when n is 58, she still owes $271 basically. So she's going to have to make a 59th payment, but it's just going to be a partial payment, so she doesn't even owe $400 anymore. So she will make 58 full payments, and then we'll notice on the 59th payment, if she paid the full $400, she'd actually be overpaying. She'd have a negative balance. So plus 1 partial payment. So really a total of 59 months to a 0 balance. All right, so there's a couple of applications of sequences that you can see. The next thing I'd like to turn to is the definition of what might be a new function for you, but it's one that's going to turn out to be pretty useful that we'll use quite a bit in our upcoming examples in this chapter. Next couple of chapters, in fact. This is called a factorial notation. And here's the definition of a factorial function. It uses the exclamation point, and this is read as n factorial. And what we do is we take the number n, and we multiply it by 1 less, 2 less, 3 less, etc., down to 1. This factorial function is defined where n is any integer greater than or equal to 1. So let's take a look at finding factorials, just to get you used to this. By the way, 0 factorial by definition is 1. It's one that doesn't make any sense based on our explanation of how to calculate it, but by definition, we consider 0 factorial to be 1. 1 factorial is just 1. 2 factorial is going to be 2 times 1, or 2. 3 factorial, start with 3 times 2 times 1. 6. If that is 4, 4 factorial, 4 times 3 times 2 times 1, 24. 5 factorial, 5 times 4 times 3 times 2 times 1 is 120. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, you're getting the idea, I'm sure, is 720. Our 7 factorial, let's write it out. And that's as high as I know them, so I'm going to use my calculator to do that. Notice it's just the 720 times 7. Uh, 5,040. And then 8 factorial would just start with the 8. And again, you're always working your way all the way down to 1. So that'd be 7 factorial times another 8 is 40,320. Okay, so that's how calculator, or how we find factorials. That's the definition of them, how they look. And one thing I do want you to notice is that as a function, factorials grow quite fast, right? Those n factorial values are pretty big. By the way, your calculator does have a factorial function. It's in your math menu. And I think, isn't it there? it was there. Well, I know it's somewhere. It has it. Oh, it might be here. There it is. Okay, start that over. In your math menu, go to PRB, stands for probability, because this gets used in probability a lot. And you'll see that factorial button right there, option number 4. So if I wanted to just check my answer to 8 factorial, let's say, I'd have 8. I'd go to that math menu, over to PRB, and down here to option 4, factorial. And there's 8 factorial. So the calculator will do it. But to use factorials algebraically, it's really important to understand how they're calculated. And here's what I mean by that. Down in this next couple of examples, the algebra of factorials, we'd like to simplify each expression and write the final answer without using any factorial notation. Let's think about what this really means. For now, I'm going to leave the n factorial the way it is, and I'm going to start writing out the bottom. N plus 2. Then they keep on going down. N plus 1. N minus 1. N minus 2. All the way down to 3 times 2 times 1. Looks like a mess. But take a closer look at all of this. What is that? Isn't all of this just n factorial? It's the product of n all the way down to 1. That's n factorial. So what I actually have here is an n factorial on the top over n plus 2, n plus 1 times n factorial. Perfect. Now we can go ahead and divide out the n factorials, top and bottom. And so the simplified version is just going to be 1 over n plus 2 times n plus 1. All right. So breaking things down, recognizing those factorials when you see them. Very important. All right, what about the next one? Well, let's see. I'm going to go ahead and start breaking down the factorials. Top would be n minus 1, n minus 2, n minus 3, etc. Down to 3 times 2 times 1. The bottom. 3 factorial is 6. And then n minus 3 factorial, n minus 3, n minus 4, and so on, down to 3 times 2 times 1. All of this is the same as all of that, right? I didn't happen to write the n minus 4 on the top, but it would have been the next term. So, in fact, I could divide all of that out of there. And I simply end up with n minus 1, n minus 2 over 6. All right. Next, just to get a bit more comfortable with factorials, we're going to try and go ahead and I'm going to give you some sequences and we're going to try to use factorials to write the expression. An explicit formula for each sequence, specifically using factorial notation. We're then going to kind of make a guess about the limit of each sequence. We don't yet have any theorems or ways of actually calculating the limits, but in many cases we can just kind of guess based on what we see. So here we go. On this one, A sub n, the sequence, is going to be, well, the first thing I notice here is that this is an alternating sequence, positive, negative, positive, negative. So for sure, we're going to want -1 to the n in here. And we may or may not need to adjust that. Let's talk about that kind of after we've got the rest of it. All right, take a look at these denominators. This is really a 1 at the bottom. Aren't those just the exact values of all the factorials if you look at the table right at the top of this page that we filled in? That's 1 factorial, 2 factorial, 3 factorial, and so on. So the denominators of all of these fractions, just n factorial. So I'm going to write that as 1 over n factorial. Okay. Now the only thing I need to make sure of is that the sign is right, and I think right now it's actually backwards. When n is odd, like a first power, it should be a positive term, and this is going to make it negative. So I can fix that just by putting a little +1 in that exponent. Now when n is 1, 1 plus 1 is 2. -1 squared is positive, just like we expected. Still alternates, just alternates in the opposite direction. So there we go. There is an explicit formula for that sequence. Now just looking at these numbers, it certainly appears that while the constant 1 is always in the numerator, the denominators keep getting bigger and bigger. So it sort of feels like this is going to 1 over infinity, which would mean that the limit of our sequence of A sub n's is probably going to be 1 over infinity or 0. All right, sorry for the ugly page break here. Let's try a few more. In B, looking at those, and right now I'm not really seeing those factorial values, but on a closer look, if I were to write this as 2 times 2, and then 2 times 6, and that one would be 2 times 24, 2 times 120, and so on, I can once again recognize the values of all those factorials right from our table, right? Every single one of these is a factorial. So let's see, this would be 2 times n factorial. These are all the factorials. But this time I do have to be a little bit careful. Up until now, we've pretty much always been able to just say, hey, let's go ahead and start with n equal 1. Right here, we started with n equal 1, 1 factorial in the denominator, so on. Here, our first value is actually 2 factorial, and then 3 factorial, and 4 factorial, and so on. So I'm going to add a little n equals 2 to infinity out here, just so that my reader knows that I didn't start at 1. Again, I didn't bother writing that here. I could have. I could have written this as n equals 1 to infinity. But kind of the generic leaving it off, that's the assumption that n would go from 1 to infinity. I typically only bother to write this when I need something else. And in this case I do, and had to start at 2. All right. Let's look at the next one. Thinking of this as 3 over 1, Definitely seeing those factorials in the denominators again. So whatever happens, I'm pretty sure I'm going to have n factorial on the bottom. Now what about the top? Do you recognize all of those as powers of 3? 3 to the first, 3 to the second, 3 to the third, and so on? So this would just be 3 to the n power. All right, one more. This time, I'm seeing my factorials in the numerators. So let's put n factorial on top this time. Okay. On the bottom, this first one would be 1. And then I have to identify what's going on with these numbers. I'm fairly certain these are all 4th powers. 1 to the 4th, 16 is 2 to the 4th, 81 is 3 to the 4th, and so on. So my denominator this time is going to be n raised to the 4th power. N does start at 1 this time, so I don't have to bother specifying.